Now, we can talk of what is called tiling the time frequency plane. It essentially means covering this plane with such rectangles, with rectangles corresponding to functions. In fact, I will say rectangular tiles. Corresponding to such functions. And what we are essentially saying is that when we take the dot product of such a function, let's be specific. So, when we take any other function, to be analyzed, let us say y of t, and let this tool function, so to speak, be x of t. Then Parseval's theorem says that if I take the dot product of y t with x t, essentially y t x bar t d t, then the same thing happens in the frequency domain. Parseval's theorem says this is equal to 1 by 2 pi. Do not worry about the factor 1 by 2 pi, it is essentially just a normalizing constant. The important thing is inside. Fourier transform of y, Fourier transform of x complex conjugated integrated over omega. So, what this means physically is, if I take the dot product, or if I take the projection of a function y t on such a tool function x t in time, I am doing the same projection in frequency. So, by projecting this y t on x t in time, I am essentially extracting information about y t in a time region between t 0 minus sigma t and t 0 plus sigma t. Parseval's theorem tells me simultaneously I am also extracting information of the Fourier transform of y in a region captured between capital omega 0 minus sigma omega and capital omega 0 plus sigma omega. Simultaneously, I am extracting information in the time frequency plane about y t in that rectangle using a tool function. So, when I take the dot product of y t with such a tool function, I am immediately extracting information about y t in that rectangle of the time frequency plane. And now, we have an interpretation. The rectangular region over which you want to extract information about a function y t cannot be smaller in area than 2 units. Well, the number 2 is not the point. I mean, you can always change that number by changing the unit. We have used a certain unit here. In fact, we have used angular frequency as far as frequency goes. If you used Hertz frequency, you would get a different number there. That is not the point. The point is that there is a minimum rectangular area over which you can view y t. There is a minimum joint resolution, there is, in the sense you cannot go finer than that resolution when you look at the two domains together. But the good news is that there are many different ways in which you can look at a small domain when it is within that uncertainty limit. In fact, now tiling has a different interpretation. if I wish to analyze a function, I think of the function in the time domain and in the frequency domain together. So, essentially I am viewing the function in a joint domain and I wish to see how the function looks in a joint domain. Let me give an example. Suppose I have what is called a chirp function. A chirp function is named after the sound of birds. When birds chirp, broadly or crudely, the chirp waveform has a pattern which is a continuously changing frequency in time, instantaneous frequency. So, it is something of the form, say sin omega as a function of t. So, essentially this instantaneous frequency, so to speak, of the sine wave is a function of time. Now, an important question in analyzing chirp functions that one encounters sometimes in radar or in sonar is trace this variation of the instantaneous frequency in time, and there the uncertainty principle hits hard. So, what we are saying is, in the time frequency plane, suppose omega t is a constant function of time, is a constant function of time, then we are talking about a frequency independent of time. Suppose that is a linear function of time, which is often true. Something like, say, this omega as a function of t is some a plus b t. This is called a linear chirp. What would you try to do with a tool? You would try to trace this pattern, and that is where the uncertainty principle hits you. It says that you can only put rectangles that look something like this. And you can never really trace what is happening within that rectangle. So, you could crudely say, if the rectangles, suppose you think of putting many rectangles on this time frequency plane, so you had rectangles like this, put them all over, and you would see that these rectangles are lighted up, so to speak. So, I will shade these. The shaded rectangles are lighted up. Or in other words, if I looked at the dot product of this function y t, which has this linear chirp nature, with this set of tiles, that means many of these functions which are on different tiles in this time frequency plane. The tiles in which the function essentially is prominent would be lighted up, that means the magnitude would be large there, the intensity would be large of the dot product. Now, all that would indicate is that it would show you discrete points. So, here for example, if you look back at this time frequency plane, each of these rectangles would correspond to a single point here. So, it would show this point and this point, the ones that lie on the line as lighted up. All right. So, these points would be lighted up here, but you cannot go closer than these points. So, of course, these points would lie on what can be seen to be a straight line, but you would not know what has happened between the points. That is what the uncertainty principle says. You cannot get instantaneous frequency as a function of time exactly, but you can do it as closely as you desire by taking smaller rectangles, and the smaller the area of the rectangles that you take to within, of course, the uncertainty principle, the better you can make this estimate. One of the meanings of a time frequency plane and its tiling. We shall see more in the next lecture. Thank you.